Long before the universe sparkled with galaxies and stars, it existed in a state of profound darkness, a time when light itself had yet to be born. This was the cosmic dawn, an era shrouded in mystery, where the universe was a silent, empty void. But how did we go from that endless night to the vibrant cosmos we see today? What sparked the first stars? And what can this ancient epoch tell us about the origins of everything we know? In this video, we're traveling back to the very beginning, to a time before time as we understand it. We'll uncover the groundbreaking discoveries that are reshaping our understanding of the universe's infancy, explore the cutting-edge tools scientists used to peer into this distant past, and reveal the secrets of how darkness gave way to light. This isn't just a story about stars, it's the story of us, of how the universe laid the foundation for life, planets, and the very fabric of existence. So let's dive into the mysteries of the cosmic dawn and discover how the universe began its journey from nothingness to everything. The story of the cosmic dawn begins with the Big Bang, an event so monumental that it still shapes the universe we see today. Picture this: around 13.8 billion years ago, the universe burst into existence, not in a place, but as a place, a tiny, unimaginably hot and dense point of energy. In the first moments, it was a chaotic frenzy of particles and radiation, expanding faster than the speed of light. As the universe stretched and cooled, it began to settle into a more stable state. Protons and electrons, once too energetic to stay together, finally combined to form the first atoms, mostly hydrogen, the simplest and most abundant element with a sprinkle of helium. But even as the universe began to take shape, it was still cloaked in darkness. For hundreds of millions of years, this primordial cosmos was a vast, featureless expanse, devoid of stars or galaxies. Scientists call this era the Dark Ages, a time when the universe was filled with nothing but clouds of hydrogen gas, drifting silently in the void. No light pierced through this gloom because there were no stars to ignite it. The universe was like a blank canvas, waiting for the first brushstroke of creation. So, what changed? What force or event could transform this shadowy realm into the luminous universe we know today? The answer lies in the birth of the first stars, an event that marked the end of the Dark Ages and the dawn of a new cosmic era. But how did these stars form in a universe that was still so young and so empty? To understand this, we need to explore the subtle shifts in the early universe, tiny fluctuations in density that would eventually become the seeds of galaxies. These small ripples, born from the chaos of the Big Bang, began to pull matter together, slowly but surely, until gravity took hold and lit the first spark of starlight. This transition from darkness to light wasn't instant. It was a gradual process, one that unfolded over millions of years, driven by the delicate interplay of physics and chance. And it's this process, the emergence of the first stars, that marks the true beginning of the cosmic dawn. But to fully grasp its significance, we need to look even closer at the forces at play in this ancient, formative era. The Dark Ages of the universe might sound like a time of stagnation, but in reality, it was a period of quiet transformation, a cosmic waiting game where the foundations of everything we see today were being laid. Imagine a universe that's cold, dark, and almost eerily still. No stars twinkling in the distance, no galaxies swirling in the void, just vast clouds of neutral hydrogen gas drifting aimlessly through the emptiness. This was the universe's adolescence, a time when it was gathering its strength, preparing for the next great leap in its evolution. But why does this seemingly featureless era matter? What makes it so important in the grand story of the cosmos? The answer lies in the subtle, almost imperceptible changes happening within those clouds of hydrogen. Gravity, the universe's great architect, was quietly at work. tiny fluctuations in the density of matter, remnants of the Big Bang's chaotic energy, began to pull these gas clouds together. Over millions of years, these small ripples grew, slowly but surely, into denser clumps of matter. This was the universe's way of laying the groundwork for the stars and galaxies that would soon burst into existence. Studying this dark, silent era is no easy task. With no light to guide us, how can we peer back into a time when the universe was essentially invisible? Scientists rely on two key tools, the cosmic microwave background, or CMB, and the faint signals emitted by neutral hydrogen. The CMB is like a snapshot of the universe's infancy, a faint afterglow of the Big Bang that carries imprints of those early density fluctuations. It's a treasure trove of information, offering clues about how matter was distributed in the primordial cosmos. Neutral hydrogen, on the other hand, emits a faint radio signal at a specific wavelength, known as the 21-centimeter line. This signal, though incredibly weak, is like a whisper from the distant past, a message from the dark ages that reaches us across billions of years. By detecting and analyzing these signals, researchers can map the distribution of hydrogen gas during this era, revealing how gravity sculpted the universe's first structures. The Dark Ages may have been a time of darkness, but it was far from uneventful. It was a cosmic interlude, a necessary pause that allowed the universe to prepare for its next act. And what an act it would be, the birth of the first stars, an event that would shatter the silence and ignite the cosmos with light. But before we get to that moment of cosmic awakening, we need to understand the forces and processes that made it possible. What triggered the collapse of those hydrogen clouds? How did the universe transition from simplicity to complexity? These are the questions that take us to the heart of the cosmic dawn. The moment the first stars ignited was nothing short of a cosmic revolution. These ancient beacons, known as population Roman 3 stars, were the universe's first true light sources, and they were unlike anything that exists today. Born from the simplest ingredients, pure hydrogen and helium, they carried no trace of heavier elements which hadn't yet been forged in the hearts of stars. This purity gave them a unique identity, setting them apart from the stars that would come later. Population Roman 3 stars were colossal, dwarfing even the largest stars in our modern skies. Imagine stars hundreds of times more massive than our Sun, burning fiercely and radiating an intense ultraviolet light that could pierce through the darkness of the early universe. But their brilliance came at a cost. These stars lived fast and died young, their enormous size driving them to consume their fuel at an astonishing rate. Within just a few million years, they exhausted themselves, ending their lives in spectacular supernovae that scattered the first heavy elements into the cosmos. The birth of these stars was a turning point, not just for the universe, but for the story of existence itself. As they blazed into life, their ultraviolet light began to interact with the surrounding hydrogen gas, stripping electrons from atoms in a process called ionization. This was the beginning of reionization, a transformative phase that turned the universe from a neutral sea of hydrogen into an ionized plasma. It was a slow, gradual process, but one that would ultimately make the cosmos transparent to light, paving the way for galaxies, planets, and life itself. But how did these first stars form in a universe that was still so young and sparse? The answer lies in the delicate dance of gravity and density. In the early universe, tiny ripples in the distribution of matter, echoes of the Big Bang, began to amplify. These ripples acted as seeds, drawing in hydrogen and helium gas over millions of years. As these clouds grew denser, gravity's pull became stronger, compressing the gas until it reached a critical point. Heat and pressure mounted, and deep within these collapsing clouds, the first stars ignited. What made population Roman 3 stars so extraordinary wasn't just their size or their light, it was their role as cosmic pioneers. They were the universe's first factories, forging elements like carbon, oxygen, and nitrogen in their cores and scattering them into space when they exploded. These elements would later become the building blocks of planets, life, and even us. Without these ancient giants, the universe as we know it simply wouldn't exist. Yet, as monumental as their birth was, it's a story that's still being uncovered. Population Roman 3 stars have never been directly observed, as they burned out long before galaxies like ours took shape. But their fingerprints are everywhere, etched into the fabric of the cosmos. Through computer simulations, observations of distant galaxies, and the faint echoes of reionization, scientists are piecing together the tale of these first stars and their profound impact on the universe. Their story is a reminder of how even the most distant and seemingly unreachable moments in cosmic history are deeply connected to our own existence. The light of the first stars didn't just illuminate the early universe, it set the stage for everything that would follow. And as we continue to unravel their mysteries, we're not just learning about the past, we're discovering the origins of our own cosmic home. The story of population Roman 3 stars is one of cosmic extremes, stars so massive and brilliant that they defy our modern understanding of stellar behavior. These ancient giants, born from the simplest elements in the universe, were hundreds of times more massive than our Sun, burning at temperatures so intense that their light could ionize the surrounding hydrogen gas. Their formation was a delicate process driven by the collapse of dense clouds of hydrogen and helium. As gravity pulled these clouds together, they fragmented into clumps, each one destined to ignite as a star. But these weren't just any stars, they were the universe's first, and their birth marked a turning point in cosmic history. What made these stars so extraordinary wasn't just their size or their heat, it was their role as cosmic alchemists. Inside their cores, hydrogen fused into helium, releasing vast amounts of energy. But their true legacy lies in what happened next. As they burned, they began to forge heavier elements like carbon and oxygen in a process known as nucleosynthesis. These elements, though sparse at first, were the seeds of complexity, the raw materials that would eventually form planets, moons, and even life. Yet, the lives of population Roman 3 stars were as brief as they were brilliant. Their enormous size meant they consumed their fuel at an astonishing rate, burning out in just a few million years. When they reached the end of their lives, they didn't fade quietly into the void. They erupted in cataclysmic supernova, scattering their newly forged elements across the cosmos. These explosions were more than just spectacular displays of cosmic power. They were the universe's first recycling program, spreading the building blocks of future stars and galaxies far and wide. The legacy of population Roman 3 stars is written in the stars and planets we see today. Without their explosive deaths, the universe would have remained a sea of hydrogen and helium, devoid of the rich tapestry of elements that make up our world. Every atom of carbon in your body, every molecule of oxygen in the air you breathe, can trace its origins back to these ancient giants. They were the pioneers of complexity, the architects of a universe that could one day give rise to life. But their story doesn't end with their destruction. The elements they created became the raw materials for the next generation of stars, known as population Roman 2 stars, and eventually for stars like our Sun, which belong to the population I category. Each generation of stars built upon the work of the last, creating a cosmic cycle of birth, death, and rebirth. Population Roman 3 stars may be long gone, but their influence is still felt across the cosmos. Through computer simulations and observations of distant galaxies, scientists are piecing together the story of these ancient giants, uncovering clues about how they shaped the universe. And as we learn more about them, we're not just uncovering the history of the cosmos, we're discovering the origins of everything we know. Their story is a reminder of how interconnected the universe truly is. The light of the first stars didn't just illuminate the early cosmos, it set the stage for the evolution of galaxies, planets, and life itself. And as we continue to explore their legacy, we're not just looking back in time, we're uncovering the foundations of our own existence. As the first stars began to shine, their light didn't just illuminate the cosmos, it fundamentally transformed it. This transformation is known as reionization, a pivotal chapter in the universe's history that marked the end of the Dark Ages and the dawn of a new era. Reionization was the process by which the intense ultraviolet light from the first stars and galaxies ionized the neutral hydrogen gas that filled the early universe. Imagine a vast, dark ocean suddenly pierced by countless beams of light, slowly turning the water from murky to clear. That's what reionization did for the cosmos. It made the universe transparent, allowing light to travel freely for the first time. But how did this process unfold? To understand reionization, we need to dive into the physics of light and matter. Neutral hydrogen gas, which dominated the early universe, absorbs ultraviolet light, trapping it and preventing it from traveling far. But when the first stars and galaxies began to emit powerful ultraviolet radiation, they stripped electrons from hydrogen atoms, turning the gas into an ionized plasma. This ionized gas no longer absorbed light as effectively, allowing photons to travel vast distances without being absorbed. The universe, once opaque, became a place where light could finally shine through. The process of reionization wasn't instantaneous. It unfolded over hundreds of millions of years, beginning around 200 million years after the Big Bang and lasting until about 1 billion years later. But what drove this transformation? The answer lies in the growing population of stars and galaxies. As more stars formed, their combined ultraviolet output grew stronger, creating expanding bubbles of ionized gas around them. These bubbles eventually overlapped, merging to form a fully ionized universe. To piece together this timeline, scientists rely on some of the most distant objects in the cosmos, quasars and ancient galaxies. Quasars, the brilliant cores of distant galaxies powered by supermassive black holes, act like cosmic lighthouses. Their light travels billions of years to reach us, passing through the remnants of neutral hydrogen gas along the way. By analyzing how this light is absorbed, researchers can map the distribution of neutral hydrogen and trace the progress of reionization. Similarly, observations of early galaxies reveal how their ultraviolet light contributed to the ionization process. Reionization wasn't just a cosmic light show, it was a critical step in the evolution of the universe. By clearing away the fog of neutral hydrogen, it set the stage for the formation of galaxies like our own Milky Way. Without reionization, the universe would have remained shrouded in darkness, unable to support the complex structures we see today. Yet, even as we uncover the story of reionization, questions remain. How did the first stars and galaxies generate enough ultraviolet light to ionize the entire universe? What role did supermassive black holes play in this process? And why did reionization take so long to complete? These mysteries drive scientists to push the boundaries of our understanding, using advanced telescopes and simulations to peer deeper into the past than ever before. Reionization reminds us that the universe is a dynamic, ever-changing place, shaped by the interplay of light, matter, and time. It's a story of transformation, of darkness giving way to light, and of a cosmos that grew increasingly complex with each passing epoch. As we continue to explore this pivotal era, we're not just uncovering the history of the universe, we're discovering the forces that shaped the very fabric of existence. As we delve deeper into the story of the cosmic dawn, there's an invisible force at play, one that shaped the universe in ways we're only beginning to understand. Dark matter, the enigmatic substance that makes up the majority of the universe's mass, was a silent yet powerful player in the birth of the first stars and galaxies. Though we can't see it or detect it directly, its influence is written across the cosmos, etched into the very fabric of the early universe. To grasp the role of dark matter, let's step back for a moment. Imagine the early universe as a vast, empty stage. Ordinary matter, the hydrogen and helium gas that would eventually form stars, was spread thinly across this stage like a faint mist. Gravity, the force that pulls matter together, was too weak to gather this gas into dense clumps on its own. But dark matter changed everything. While ordinary matter interacts with light and other forces, dark matter only feels gravity. This meant it could clump together long before ordinary matter, forming invisible scaffolds that would later guide the formation of stars and galaxies. These dark matter structures acted like cosmic blueprints. As they grew denser, their gravitational pull attracted hydrogen and helium gas, drawing it into the same regions. Over time, these clouds of gas became dense enough to collapse under their own gravity, igniting the first stars. Without dark matter, the universe might have remained a diffuse, featureless expanse, with gas too scattered to form anything as complex as a star. It was the gravitational hand of dark matter that gathered the raw materials of creation, setting the stage for the cosmic dawn. Yet, for all its importance, dark matter remains one of the greatest mysteries in science. We know it exists because of its gravitational effects. Galaxies spin faster than they should, and clusters of galaxies bend light in ways that can't be explained by visible matter alone. But what is it made of? How does it interact with the rest of the universe? These questions are at the forefront of cosmology, driving scientists to develop new ways to detect and study this elusive substance. One of the most fascinating aspects of dark matter is its role in the cosmic dawn. By mapping the distribution of dark matter in the early universe, researchers can trace how it influenced the formation of the first stars and galaxies. Computer simulations reveal that dark matter formed a vast web-like structure with filaments connecting dense knots of matter. These knots became the seeds of the first galaxies, while the filaments channeled gas into the regions where stars would eventually ignite. The interplay between dark matter and ordinary matter was a delicate dance, one that shaped the universe on both the largest and smallest scales. On one hand, dark matter's gravitational pull created the conditions for star formation. On the other, it dictated the overall structure of the cosmos, determining where galaxies would form and how they would evolve. This dual role makes dark matter not just a cosmic architect, but a key to understanding the universe's origins. As we continue to explore the mysteries of dark matter, we're not just uncovering the history of the cosmos, we're probing the very nature of existence. What is the universe made of? How did it evolve from a formless void to the intricate tapestry we see today? Dark matter holds the answers to these questions, and as we piece together its story, we're drawing closer to understanding the forces that shaped our cosmic home. The cosmic dawn was a time of transformation, a moment when the universe began to take shape. And at the heart of this transformation was dark matter, the unseen force that made it all possible. As we peer deeper into the past, we're reminded that the universe is far more complex and far more mysterious than we could have imagined. And in that mystery lies the promise of discovery, a chance to unravel the secrets of the cosmos and our place within it. With the first stars lighting up the cosmos, the universe was no longer a place of darkness and silence. It was beginning to take shape, but stars didn't exist in isolation. Drawn together by gravity, they began to cluster, forming the earliest galaxies. These weren't the majestic spirals or glowing ellipticals we see today. The first galaxies were small, chaotic, and irregular, more like flickering fireflies in a vast, empty sky than the grand structures we associate with the word galaxy. Yet, despite their modest beginnings, these early galaxies were the building blocks of everything that followed. The formation of the first galaxies was a natural next step in the universe's evolution. As stars formed within dense clouds of hydrogen gas, their combined gravity pulled more gas and stars into their orbits, creating small, tightly bound systems. Over time, these systems grew, merging with one another to form larger structures. This process wasn't quick. It unfolded over hundreds of millions of years, driven by the relentless pull of gravity. And as galaxies grew, they began to shape the universe around them, carving out the first threads of what would become the cosmic web. What's fascinating about these early galaxies is how different they were from the ones we see today. Without heavy elements like carbon, oxygen, and iron, which were forged in the hearts of stars, they were made almost entirely of hydrogen and helium. Their stars burned hotter and brighter, their shapes were less defined, and their structures were far more turbulent. Yet, within this chaos, the seeds of complexity were sown. These galaxies weren't just collections of stars, they were the first steps toward a universe rich with diversity and structure. Studying these ancient galaxies is like looking through a time machine. By observing the most distant galaxies, astronomers can peer back to a time when the universe was still in its infancy. The light from these galaxies has traveled billions of years to reach us, carrying with it clues about how they formed and evolved. One of the most powerful tools for this research is the James Webb Space Telescope, which can detect the faint glow of galaxies that existed just a few 100 million years after the Big Bang. These observations are helping scientists piece together the story of how small, irregular clumps of stars grew into the vast, intricate galaxies we see today. But the story of the first galaxies isn't just about their size or shape. It's about their role in shaping the universe. As galaxies formed and grew, they began to interact with one another, merging and colliding in a cosmic dance that continues to this day. These interactions weren't just destructive, they were creative, triggering bursts of star formation and fueling the growth of supermassive black holes at the centers of galaxies. Over time, these processes gave rise to the diverse array of galaxies we see in the modern universe, from spirals like our Milky Way to giant ellipticals and irregular galaxies. The first galaxies also played a crucial role in the process of reionization. As their stars emitted ultraviolet light, they helped ionize the surrounding hydrogen gas, clearing the way for light to travel freely through the cosmos. This marked the end of the Dark Ages and the beginning of a new era, one in which galaxies became the dominant structures in the universe. What can these ancient galaxies teach us about our own cosmic home? By studying their formation and evolution, scientists can trace the origins of galaxies like the Milky Way, understanding how they grew from small, chaotic systems into the grand spirals we see today. They also provide clues about the universe's large-scale structure, the vast web of galaxies, clusters, and voids that stretches across the cosmos. The first galaxies were more than just collections of stars. They were the architects of the universe's complexity. Through their growth and interactions, they shaped the cosmos, setting the stage for everything that would come after. And as we continue to explore their story, we're not just uncovering the history of the universe, we're discovering the origins of our own place within it. The cosmic microwave background, or CMB, is like a time capsule, a faint whisper from the universe's infancy. This ancient light, the oldest we can observe, is a remnant of the Big Bang itself, a glowing echo from a time when the cosmos was just 380,000 years old. Imagine holding a photograph of the universe as a newborn, its features still soft and undefined, yet already hinting at the complexity to come. That's what the CMB offers, a snapshot of the universe at its most primal, capturing the moment when it transitioned from a hot, dense plasma to a cooler, more transparent state. But how does this faint glow help us understand the origins of the cosmos? the CMB isn't just a relic of the past, it's a treasure trove of information encoded with clues about the universe's earliest moments. When the universe was young, it was filled with a searing, opaque soup of particles and radiation. As it expanded and cooled, protons and electrons combined to form neutral hydrogen, allowing light to travel freely for the first time. This light, now stretched and cooled by billions of years of cosmic expansion, reaches us as the CMB, a faint microwave glow that permeates the entire sky. What makes the CMB so extraordinary is its uniformity. At first glance, it appears almost perfectly smooth, a testament to the universe's early state of near equilibrium. But upon closer inspection, tiny fluctuations in temperature, just 1 part in 100,000, reveal the seeds of future structures. These minuscule ripples, imprinted by quantum fluctuations in the early universe, are the blueprints for everything we see today. They mark the regions where matter was slightly denser, destined to grow under gravity's pull into galaxies, clusters, and the vast cosmic web. By studying these fluctuations, scientists can reconstruct the universe's early history with remarkable precision. The CMB acts as a kind of cosmic fingerprint, revealing the fundamental properties of the universe, from its composition to its age and rate of expansion. It tells us that dark matter and dark energy dominate the cosmos, shaping its evolution in ways we're still working to understand. It also provides a timeline, helping us trace the universe's journey from the Big Bang to the cosmic dawn and beyond. One of the most profound discoveries from the CMB is the evidence it provides for cosmic inflation, a theory that suggests the universe underwent an exponential expansion in the first fraction of a second after the Big Bang. This rapid stretching would explain why the CMB is so uniform and why the universe appears flat on large scales. It's a theory that connects the tiniest quantum fluctuations to the largest structures in the cosmos, offering a glimpse into the universe's first moments. Yet, the CMB isn't just a tool for studying the ancient past, it's also a window into the universe's future. By measuring the subtle patterns in this ancient light, scientists can test theories about dark energy, the mysterious force driving the universe's accelerating expansion. They can also explore the nature of dark matter, the invisible scaffolding that shaped the first galaxies. In this way, the CMB bridges the gap between the universe's birth and its ultimate fate, offering insights that span the entirety of cosmic history. The story of the CMB is one of discovery and connection. It reminds us that the universe is a tapestry woven from the threads of its earliest moments, with each thread carrying clues about the forces that shaped it. And as we continue to study this ancient light, we're not just uncovering the origins of the cosmos, we're piecing together the story of our own existence. The CMB is more than a relic of the past, it's a map of the universe's journey, a guide to the mysteries that still lie ahead. Hidden within the faint whispers of the cosmos lies a signal so subtle, so delicate, that it has the power to unlock the secrets of the universe's darkest era. This is the 21-centimeter line, a faint radio emission from neutral hydrogen gas that has traveled across billions of years to reach us. It's a time capsule from the Dark Ages, carrying with it clues about the temperature, density, and structure of the early universe. Imagine listening to a faint, ancient melody, one that tells the story of a time when stars had yet to ignite and the universe was cloaked in silence. That's what the 21-centimeter line offers, a direct connection to the universe's infancy. But why is this signal so important? To answer that, we need to understand how it's created. Neutral hydrogen, the simplest and most abundant element in the early universe, emits a faint radio signal when the spin of its electron flips. This flip releases a photon with a wavelength of 21 centimeters, a whisper of energy that can travel vast distances through space. Because this signal is so specific, it acts like a cosmic fingerprint, allowing scientists to map the distribution of hydrogen gas during the Dark Ages and the cosmic dawn. The 21-centimeter line is more than just a signal, it's a window into a time when the universe was still taking shape. By studying its variations, researchers can reconstruct the temperature and density of the early universe, revealing how matter clumped together under gravity's pull. These subtle ripples in the hydrogen gas were the seeds of the first stars and galaxies, and the 21-centimeter line allows us to trace their growth in unprecedented detail. Detecting this signal, however, is no easy task. The 21-centimeter line is incredibly faint, drowned out by the noise of modern radio emissions from Earth and even the Milky Way. To overcome this challenge, scientists are building some of the most advanced radio telescopes ever conceived. One of the most ambitious projects is the Square Kilometre Array, or SCAR, a sprawling network of antennas that will span 2 continents. When completed, the SKA will be the largest and most sensitive radio telescope in the world, capable of detecting the 21-centimeter line with unparalleled precision. What makes the SKA so exciting is its potential to map the universe's hydrogen distribution in 3 dimensions. By observing how the 21-centimeter line changes over time, astronomers can create a timeline of the Dark Ages and the cosmic dawn, charting the transition from a universe of darkness to one filled with light. This could reveal not only how the first stars formed, but also how they interacted with their surroundings, ionizing the hydrogen gas and ending the Dark Ages. The 21-centimeter line also holds clues about the role of dark matter in the early universe. By comparing the distribution of hydrogen gas with simulations of dark matter's influence, scientists can test theories about how these 2 invisible forces shape the cosmos. It's a way to peer into the universe's hidden architecture, uncovering the scaffolding that supported the birth of stars and galaxies. But the 21-centimeter line isn't just a tool for studying the past, it's also a way to explore the universe's future. By measuring how the signal evolves over time, researchers can test theories about dark energy, the mysterious force driving the universe's accelerating expansion. It's a reminder that the cosmos is a dynamic, ever-changing place, and that even the faintest signals can carry profound insights. As we continue to develop the technology to detect and analyze the 21-centimeter line, we're not just uncovering the history of the universe, we're rewriting it. Every new observation brings us closer to understanding how the cosmos transitioned from darkness to light, from simplicity to complexity. And in that understanding, we find not just the origins of the universe, but the origins of ourselves. The 21-centimeter line is more than a scientific tool, it's a bridge to the past, a connection to a time when the universe was still finding its way. And as we listen to its faint whispers, we're reminded that the story of the cosmos is still being written, with each discovery adding a new chapter to the grand narrative of existence. To unravel the mysteries of the cosmic dawn, scientists have turned to some of the most powerful tools at their disposal: supercomputers. These machines, capable of performing trillions of calculations per second, allow researchers to recreate the early universe in extraordinary detail. By simulating the conditions that existed billions of years ago, they can explore how the first stars and galaxies formed and how they shaped the cosmos we see today. It's like building a time machine out of code, one that lets us witness the birth of the universe from the comfort of our own planet. These simulations begin with the raw ingredients of the early universe: hydrogen and helium gas, dark matter, and the faint ripples left over from the Big Bang. Using the laws of physics, supercomputers model how these elements interacted over millions of years, tracing the growth of cosmic structures from tiny fluctuations to vast galaxies. The results are breathtaking virtual universes that evolve before our eyes, revealing the delicate interplay of gravity, gas, and light. One of the most striking discoveries from these simulations is how quickly the first stars and galaxies emerged. In a universe that was once dark and featureless, small clumps of matter began to collapse under gravity's pull, igniting stars within just a few 100 million years. These early stars were unlike anything we see today, massive, short-lived, and blazing with intense ultraviolet light. Their formation triggered a cascade of events, from the ionization of surrounding gas to the birth of the first galaxies. But the simulations don't just show us what happened, they also help us understand why. By tweaking the parameters of their models, scientists can test different theories about the early universe. For example, how did dark matter influence the formation of the first galaxies? What role did magnetic fields or cosmic rays play? These virtual experiments allow researchers to explore questions that would be impossible to answer through observation alone. What's truly remarkable is how closely these simulations match what we observe in the real universe. By comparing their results with data from telescopes like the James Webb Space Telescope, scientists can refine their models, making them more accurate and revealing new insights. For instance, simulations have helped explain why some of the earliest galaxies appear brighter than expected, suggesting that star formation in the early universe may have been more efficient than we thought. These virtual universes also reveal the complex web of connections that shaped the cosmos. As galaxies formed and grew, they didn't exist in isolation. They interacted with one another, merging and colliding in a cosmic dance that continues to this day. Simulations show how these interactions triggered bursts of star formation and fueled the growth of supermassive black holes, shaping the universe on both small and large scales. Perhaps the most profound lesson from these simulations is how interconnected the universe truly is. The formation of the first stars and galaxies wasn't just a local event. It was a cosmic process that rippled across the entire universe, setting the stage for everything that would come after. By studying these virtual universes, we're not just learning about the past, we're uncovering the origins of the cosmic web, the vast network of galaxies and voids that defines the structure of the universe today. As we continue to refine these simulations, they're becoming more than just tools for understanding the past. They're guiding our exploration of the future. By revealing the fundamental processes that shape the universe, they're helping us predict what lies ahead, from the evolution of galaxies to the fate of the cosmos itself. And in that journey, we're reminded that the story of the universe is still being written, with each simulation adding a new chapter to our understanding of existence. Through the power of supercomputers, we're able to witness the birth of the cosmos, to explore the forces that shaped it, and to uncover the origins of the stars, galaxies, and even the atoms that make up our world. It's a journey that takes us from the smallest ripples in the fabric of space-time to the vast, intricate tapestry of the universe. And it's one that continues to inspire awe and wonder with every new discovery. While black holes are often portrayed as cosmic destroyers, their role in the early universe tells a different story, one of creation and transformation. These enigmatic objects, born from the fiery deaths of the first stars, were not just passive observers of the cosmic dawn. They were active participants, shaping the universe in ways that still echo across billions of years. The first black holes, formed from the collapse of massive population Roman III stars, were unlike anything we see today. They were small but voracious, feeding on the surrounding hydrogen gas and growing rapidly. Their immense gravitational pull didn't just consume matter. It shaped the environment around them, influencing the birth of stars and the formation of galaxies. Imagine a black hole as a cosmic sculptor carving out the landscape of the early universe. As these black holes consumed gas, they released enormous amounts of energy in the form of radiation and powerful jets. This energy didn't just vanish into the void, it interacted with the surrounding gas, heating it up and preventing it from collapsing to form new stars. In some regions, this process slowed star formation, creating pockets of hot, ionized gas. In others, the shock waves from black hole activity triggered the collapse of gas clouds, sparking bursts of star formation. It's a paradox. Black holes, often seen as destructive, could also be catalysts for creation. But how did these early black holes grow so quickly? The answer lies in their environment. The early universe was rich with gas, and black holes had an almost endless supply of fuel. As they consumed this gas, they grew larger, merging with other black holes to form even more massive objects. These mergers were cosmic collisions, releasing ripples in space-time known as gravitational waves. Over time, these black holes became the seeds of the supermassive black holes we see at the centers of galaxies today. The influence of black holes extended far beyond their immediate surroundings. Their intense radiation helped ionize the hydrogen gas that filled the universe, contributing to the process of reionization. As their jets blasted through the cosmos, they carved out bubbles of ionized gas, creating pathways for light to travel freely. This wasn't just a local phenomenon, it was a large-scale transformation that helped bring the Dark Ages to an end. What's fascinating is how these early black holes interacted with the first galaxies. As galaxies formed, black holes often took up residence at their centers, growing alongside them. The relationship between black holes and their host galaxies was symbiotic. Galaxies provided the fuel for black holes to grow, while black holes regulated star formation and influenced the evolution of galaxies. This intricate dance between destruction and creation shaped the cosmos, laying the foundation for the universe we see today. Yet, for all their influence, the first black holes remain shrouded in mystery. How did they form so quickly after the Big Bang? What role did they play in the formation of the first galaxies? And how did their activity shape the large-scale structure of the universe? These are questions that scientists are still working to answer, using observations of distant quasars and simulations of the early universe. The story of black holes in the cosmic dawn is a reminder that the universe is full of surprises. Even the most seemingly destructive forces can play a creative role, shaping the cosmos in ways we're only beginning to understand. As we continue to explore their mysteries, we're not just uncovering the history of the universe, we're discovering the forces that shaped its evolution and set the stage for everything that followed. From the collapse of the first stars to the birth of galaxies, black holes were more than just cosmic phenomena. They were architects of the universe's complexity. And as we peer deeper into the past, we're reminded that even in the darkest corners of the cosmos, there's a story waiting to be told. Among the most dazzling objects in the cosmos are quasars, the brilliant beacons of the early universe. These distant powerhouses are fueled by supermassive black holes, some of which are billions of times more massive than our Sun. As matter spirals into these black holes, it heats up to incredible temperatures, releasing torrents of energy in the form of light, X-rays, and radio waves. This makes quasars some of the brightest objects in the universe, visible across billions of light years. But their brilliance isn't just a cosmic spectacle, it's a window into the universe's infancy, offering clues about the era of the cosmic dawn and the great transformation of reionization. Quasars are more than just bright lights, they're cosmic storytellers. Their light, which has traveled for billions of years to reach us, carries traces of the gas it has passed through along the way. By analyzing this light, scientists can map the distribution of hydrogen gas in the early universe, revealing how it changed over time. For example, when quasar light passes through neutral hydrogen gas, specific wavelengths are absorbed, creating a kind of fingerprint in the spectrum. This allows researchers to determine when and whether gas was ionized, piecing together the timeline of reionization. What makes quasars especially valuable is their role as lighthouses in the cosmic dark. During the early stages of the universe, much of the hydrogen gas was neutral, absorbing light and keeping the cosmos shrouded in darkness. But as quasars began to shine, their intense radiation ionized the surrounding gas, carving out bubbles of transparency. Over time, these bubbles grew and merged, helping to end the dark ages and usher in an era of light. Quasars weren't just passive observers of this process. They were active participants, driving the transformation of the universe on a grand scale. Another fascinating aspect of quasars is their connection to the growth of galaxies. The supermassive black holes at their centers didn't just consume matter, they influenced the evolution of their host galaxies. As these black holes grew, their energy output regulated star formation, heating up gas and preventing it from collapsing into new stars. In some cases, the jets of energy blasted out by quasars triggered bursts of star formation in nearby gas clouds. This delicate balance between destruction and creation shaped the early universe, leaving an imprint on the galaxies we see today. Studying quasars also provides insights into the nature of dark matter and dark energy. Their light can be bent and distorted by the gravitational pull of massive objects, a phenomenon known as gravitational lensing. By observing how quasar light is lensed, scientists can map the distribution of dark matter in the universe, revealing the invisible scaffolding that supports the cosmic web. At the same time, quasars serve as cosmic mile markers, helping to measure the expansion of the universe and probe the mysterious force of dark energy. Yet, quasars remain as enigmatic as they are luminous. How did supermassive black holes form so quickly after the Big Bang? What role did they play in the formation of the first galaxies? And how did their energy output shape the large-scale structure of the universe? These are questions that continue to drive scientific exploration, pushing the boundaries of our understanding. As we study these cosmic beacons, we're not just uncovering the history of the universe, we're piecing together the story of its transformation. From the darkness of the cosmic dawn to the light-filled cosmos we see today, quasars have played a pivotal role in shaping the universe's evolution. And as we continue to explore their mysteries, we're reminded that even the most distant and ancient objects can hold the keys to understanding our cosmic origins. Quasars are more than just bright lights in the void, they're guides, illuminating the path from the universe's infancy to its present-day complexity. Through their light, we glimpse the forces that shape the cosmos, and in that understanding, we find a deeper connection to the story of everything. The epoch of reionization stands as one of the most profound transformations in the history of the cosmos. It was a time when the universe, once cloaked in darkness, began to glow with the light of the first stars, galaxies, and quasars. But this wasn't just a shift from dark to light, it was a fundamental change in the very nature of the universe. During this epoch, the neutral hydrogen gas that filled the cosmos was ionized, its atoms stripped of their electrons, turning the universe from opaque to transparent. This transformation didn't happen overnight. It unfolded over hundreds of millions of years, driven by the intense radiation of the first luminous objects. So, what exactly triggered this cosmic metamorphosis, and how did it shape the universe we see today? The journey to reionization began with the birth of the first stars, colossal giants that burned brightly and briefly. These stars, known as population Roman 3 stars, emitted powerful ultraviolet light that began to ionize the surrounding hydrogen gas. Imagine a single candle flickering in a vast, dark room slowly, its light spreads illuminating the space around it. That's what these early stars did, creating bubbles of ionized gas that grew larger as more stars ignited. Over time, these bubbles began to overlap, merging into a vast ionized network that stretched across the cosmos. But stars weren't the only players in this cosmic drama. galaxies too played a crucial role. As the first galaxies formed, their stars collectively emitted even more ultraviolet radiation, accelerating the ionization process. These galaxies weren't isolated islands of light, they were connected by filaments of gas, forming a web-like structure that allowed ionizing radiation to travel far and wide. And then there were quasars, the brilliant powerhouses fueled by supermassive black holes. Their intense radiation carved out massive ionized regions, contributing to the growing transparency of the universe. Together, stars, galaxies, and quasars worked in concert to transform the cosmos. One of the most fascinating aspects of reionization is how it unfolded unevenly across space and time. In some regions, ionization occurred early, driven by the intense radiation of massive stars. In others, it happened later, as smaller galaxies and quasars began to contribute. This patchwork of ionized and neutral gas created a dynamic, ever-changing landscape, with pockets of darkness persisting even as the universe grew brighter. Mapping this complex process is one of the great challenges in cosmology, requiring observations of the most distant objects in the universe. To piece together the story of reionization, scientists rely on a variety of tools. Observations of distant quasars, for example, reveal how their light is absorbed by neutral hydrogen gas along the way, providing a snapshot of the ionization state of the universe at different times. Similarly, the faint glow of the cosmic microwave background carries imprints of reionization, offering clues about when and how it occurred. These observations are complemented by computer simulations, which recreate the conditions of the early universe and help researchers understand the interplay of light, gas, and dark matter. Reionization wasn't just a cosmic light show, it was a critical step in the evolution of the universe. By clearing away the fog of neutral hydrogen, it allowed light to travel freely, paving the way for the formation of galaxies like our own Milky Way. Without reionization, the universe would have remained shrouded in darkness, unable to support the complex structures we see today. It's a reminder that even the faintest light can transform the cosmos, setting the stage for the emergence of galaxies, stars, and planets. As we continue to explore the mysteries of reionization, we're not just uncovering the history of the universe, we're discovering the forces that shaped its evolution. Every observation, every simulation brings us closer to understanding how the cosmos transitioned from darkness to light, from simplicity to complexity. And in that understanding, we find not just the origins of the universe, but the origins of ourselves. The epoch of reionization was more than a cosmic transformation. It was a turning point in the story of existence. By illuminating the universe, it laid the foundation for everything that would come after, from the birth of galaxies to the emergence of life. And as we peer deeper into this ancient era, we're reminded that even the faintest light can change the course of history. The universe as we know it isn't just a scattering of stars and galaxies floating in a void. It's a grand, intricate tapestry, woven together by gravity into a structure so vast it defies imagination. This is the cosmic web, a network of filaments and voids that stretches across billions of light years. Picture it like a colossal spider's web, with galaxies and clusters of galaxies strung along its shimmering threads, connected by invisible bridges of dark matter and gas. But how did this immense structure come to be? To understand its origins, we need to travel back to the cosmic dawn, a time when the universe was still taking its first steps toward complexity. The seeds of the cosmic web were sown in the earliest moments of the universe, imprinted by the faint ripples of the Big Bang. These tiny fluctuations in density, barely noticeable at first, were the building blocks of everything we see today. As the universe expanded and cooled, gravity began to work its magic, pulling matter into denser regions. Over hundreds of millions of years, these regions grew, forming the first stars and galaxies. But gravity didn't stop there. It continued to shape the cosmos, drawing galaxies together into clusters and connecting them with vast filaments of gas and dark matter. What's fascinating about the cosmic web is how it mirrors the structure of the early universe. The filaments, often referred to as the skeleton of the universe, trace the paths along which matter flowed as it clumped together. Between these filaments lie enormous voids, regions of space that are eerily empty, containing little more than a few stray atoms. Together, these filaments and voids create a structure that's both beautiful and functional, guiding the flow of matter and energy across the cosmos. But how did this web-like structure emerge from the chaos of the early universe? The answer lies in the delicate interplay of dark matter and ordinary matter. Dark matter, invisible and mysterious, played a crucial role in shaping the cosmic web. Because it doesn't interact with light, dark matter was able to clump together long before ordinary matter, forming the first scaffolds of the web. These dark matter halos acted like cosmic magnets, drawing in gas and dust, which eventually collapsed to form stars and galaxies. As galaxies formed, they didn't just sit idly in space, they moved along the filaments, pulled by gravity toward the densest regions where clusters of galaxies began to take shape. These clusters, some containing thousands of galaxies, became the nodes of the cosmic web, the hubs where multiple filaments intersected. Over billions of years, the web grew more complex, with filaments stretching across the universe like the branches of a colossal tree. The cosmic web isn't just a static structure, it's a dynamic, ever-changing network. Galaxies and gas continue to flow along its filaments, pulled by gravity toward the densest regions. This ongoing motion shapes the evolution of galaxies, influencing how they grow, merge, and interact. It's a reminder that the universe is far from static. It's a living, breathing entity constantly in motion. Studying the cosmic web is no easy task because it's so vast it's impossible to observe directly. Instead, scientists rely on computer simulations and observations of distant galaxies to map its structure. One of the most ambitious projects in this field is the Sloan Digital Sky Survey, which has mapped the positions of millions of galaxies, revealing the intricate patterns of the cosmic web in unprecedented detail. These observations are helping scientists understand not just how the web formed, but how it continues to evolve. The cosmic web is more than just a structure, it's a testament to the universe's interconnectedness. Every galaxy, every star, and every planet is part of this vast network, connected by the invisible threads of gravity and dark matter. It's a reminder that the universe isn't just a collection of isolated objects, it's a single, unified system, shaped by the same forces that gave rise to the first stars and galaxies. As we continue to explore the cosmic web, we're not just uncovering the structure of the universe, we're discovering the story of its evolution. From the faint ripples of the Big Bang to the intricate network of filaments and voids we see today, the cosmic web tells the story of how the universe grew from simplicity to complexity. And in that story, we find not just the origins of the cosmos, but the origins of our own place within it. The cosmic web is a reminder that even the largest structures in the universe have humble beginnings. It's a story of connection, of how the universe's smallest fluctuations gave rise to its grandest designs. And as we peer deeper into its mysteries, we're reminded that the universe is far more interconnected and far more beautiful than we could have ever imagined. The moment the first stars ignited, the universe erupted into light for the very first time. These ancient beacons, known as population Roman 3 stars, were unlike anything we see in the night sky today. Born from pure hydrogen and helium, they were massive, luminous, and short-lived, burning with an intensity that defies imagination. Their light, a searing ultraviolet glow, didn't just illuminate the cosmos, it transformed it, marking the end of the Dark Ages and the beginning of a new era. This was the birth of cosmic illumination, a turning point that set the stage for everything that would come after. What made this first light so extraordinary wasn't just its brightness, it was its power to reshape the universe. As these stars blazed into existence, their ultraviolet radiation began to interact with the surrounding hydrogen gas, stripping electrons from atoms in a process called ionization. This was the dawn of reionization, a slow but relentless transformation that turned the universe from a neutral sea of hydrogen into an ionized plasma. Over hundreds of millions of years, the light from these stars carved bubbles of transparency in the cosmic fog, allowing light to travel freely for the first time. The universe, once cloaked in darkness, was becoming a place of light. But the impact of this first light didn't stop there. As it spread through the cosmos, it illuminated the earliest galaxies, revealing their chaotic, irregular shapes. These galaxies, still in their infancy, were far from the majestic spirals and ellipticals we see today. They were small, turbulent, and teeming with activity, their stars forming in bursts of intense energy. The light from population Roman 3 stars didn't just reveal these galaxies, it helped shape them, driving the processes of star formation and galaxy evolution. In this way, the first light wasn't just a passive observer of the universe's transformation, it was an active participant, a force that helped sculpt the cosmos. The nature of this light also holds clues about the early universe. Unlike the light from modern stars, which contains traces of heavier elements like carbon and oxygen, the light from population Roman 3 stars was pure, untainted by the presence of metals. This purity makes it a unique window into the universe's infancy, offering insights into the conditions that existed before the first stars formed. By studying the faint echoes of this ancient light, scientists can reconstruct the universe's earliest moments, piecing together the story of how it transitioned from darkness to light. Yet, the story of the first light is more than just a tale of cosmic transformation, it's a story of connection. The light from population Roman 3 stars didn't just illuminate the early universe, it set the stage for the emergence of galaxies, planets, and even life itself. Every star that shines today, every galaxy that glows in the night sky, owes its existence to the first light that pierced the cosmic darkness. As we continue to explore the mysteries of this ancient light, we're reminded of how interconnected the universe truly is. The first stars didn't just illuminate the cosmos, they laid the foundation for its evolution, their light echoing across billions of years to shape the universe we see today. And in that light, we find not just the origins of the cosmos, but the origins of our own existence. The birth of cosmic illumination was a moment of profound change, a turning point that reshaped the universe and set it on a path toward complexity. From the first flicker of starlight to the dazzling galaxies that fill the night sky, the story of the first light is a testament to the power of illumination and to the enduring legacy of the stars that lit the way. The universe began with just hydrogen and helium, the simplest and most abundant elements, but today we're surrounded by a rich tapestry of elements: carbon in our bodies, oxygen in the air, iron in the Earth's core. Where did all these heavier elements come from? The answer lies in the hearts of the first stars and the explosive deaths that followed. This is the story of cosmic chemistry, a process that began during the cosmic dawn and continues to shape the universe today. When the first stars ignited, they weren't just sources of light, they were cosmic alchemists. Deep within their cores, the intense heat and pressure fused hydrogen into helium, releasing energy and laying the foundation for more complex reactions. But as these massive stars burned through their fuel, they began to forge heavier elements. Helium fused into carbon, carbon into oxygen, and so on, all the way up to iron. This process, known as nucleosynthesis, is how the universe's first factories began producing the raw materials for planets, life, and everything we see around us. Yet, these early stars were more than just producers, they were also distributors. Their lives were short and fiery, ending in spectacular supernovae that scattered their newly forged elements across the cosmos. Imagine a cosmic explosion so powerful that it could fling elements like carbon, oxygen, and silicon across vast distances, seeding the universe with the building blocks of complexity. These supernovae didn't just destroy, they created, enriching the surrounding gas clouds with the ingredients for future stars, planets, and even life. But the story of cosmic chemistry doesn't end with the first stars. Each generation of stars built upon the work of the last. As new stars formed from the enriched gas left behind by supernova, they continued the process of nucleosynthesis, creating even heavier elements like gold, silver, and uranium. Over billions of years, this cycle of star birth, death, and rebirth transformed the universe from a sea of hydrogen and helium into a rich chemical landscape. One of the most fascinating aspects of this process is how interconnected it is. The carbon in your DNA, the oxygen you breathe, and the iron in your blood all trace their origins back to the hearts of ancient stars. It's a reminder that we are literally made of stardust, the products of cosmic chemistry that began billions of years ago. Scientists study this process by analyzing the light from stars and galaxies, looking for the chemical signatures of different elements. These observations reveal how the universe's chemical composition has changed over time, offering clues about the lives and deaths of the stars that came before. Computer simulations also play a crucial role, allowing researchers to recreate the conditions of the early universe and trace the evolution of cosmic chemistry. What's truly remarkable is how this process continues today. Stars in our own galaxy are still forging new elements, and supernovae are still scattering them across the cosmos. The universe is a dynamic, ever-changing place, and cosmic chemistry is at the heart of its evolution. As we explore the origins of the elements, we're not just uncovering the history of the universe, we're discovering the story of our own origins. Every atom in your body, every molecule in the world around you, carries the imprint of the stars that came before. It's a story of creation and connection, one that reminds us just how deeply we're tied to the cosmos. From the first stars to the elements that make up our world, cosmic chemistry is a testament to the universe's creativity. It's a process that began in the hearts of ancient stars and continues to shape the universe today, weaving the elements of existence into a tapestry as vast and intricate as the cosmos itself. Imagine the universe as a vast, silent ocean, its surface smooth and unbroken. Now picture a massive stone dropping into that ocean, sending ripples outward in all directions. Gravitational waves are like those ripples, but instead of traveling through water, they move through the very fabric of space-time itself. These waves are created by some of the most violent events in the cosmos, colliding black holes, merging neutron stars, and even the explosive birth of the universe itself. But what makes them so extraordinary isn't just their origin, it's what they can tell us about the early universe, a time shrouded in mystery and awe. Gravitational waves were first predicted by Albert Einstein over a century ago, but it wasn't until 2015 that scientists finally detected them, using incredibly sensitive instruments like LIGO and Virgo. These detectors, with their laser beams stretching across miles, are designed to catch the faintest tremors in space-time, ripples so subtle they can stretch and squeeze the Earth itself by less than the width of an atom. When two black holes collide, they send out a burst of gravitational waves that can travel billions of light years, carrying with them information about their origins and the nature of the universe itself. What makes gravitational waves so valuable is their ability to reveal things that light cannot. While light can be blocked or absorbed by dust and gas, gravitational waves pass through everything, offering an unobstructed view of the cosmos. This makes them an ideal tool for studying the cosmic dawn, a time when the universe was still dark and opaque. By detecting gravitational waves from the earliest black holes, scientists can learn about their formation, their masses, and even the conditions of the universe when they were born. It's like having a direct line to the universe's infancy, a way to eavesdrop on its earliest whispers. One of the most exciting possibilities is that gravitational waves could reveal the existence of primordial black holes, hypothetical objects that may have formed in the first moments after the Big Bang. These black holes, unlike the ones formed from collapsing stars, could be relics of the universe's birth, carrying clues about the extreme conditions that existed at that time. If detected, they would provide a completely new window into the early universe, helping us understand how the first structures formed and how the cosmos evolved from a hot, dense state to the intricate web we see today. But gravitational waves don't just tell us about black holes, they can also shed light on the nature of spacetime itself. Einstein's theory of general relativity predicts how gravitational waves should behave, but by studying them in detail, scientists can test whether the theory holds true under the most extreme conditions. Any deviations from Einstein's predictions could point to new physics, offering clues about phenomena we don't yet understand, like dark energy or quantum gravity. What's truly remarkable is how gravitational waves connect us to the universe's most dramatic moments. When we detect a wave from a black hole merger billions of light years away, we're witnessing an event that happened long before the Earth even existed. It's a reminder that the cosmos is constantly in motion, with stars being born, dying, and colliding in a never-ending dance. And through gravitational waves, we're not just observers of this dance, we're participants, able to feel the tremors of these cosmic events as they ripple through space-time. As we continue to refine our ability to detect and analyze gravitational waves, we're opening up a new frontier in our understanding of the universe. From the formation of the first black holes to the nature of spacetime itself, these ripples in the fabric of reality hold the keys to some of the deepest mysteries of the cosmos. And as we listen to their echoes, we're not just uncovering the history of the universe, we're discovering the forces that shaped its evolution and set the stage for everything that followed. Gravitational waves are more than just scientific tools, they're cosmic storytellers, carrying the tales of the universe's most dramatic moments across billions of years. And as we tune into their whispers, we're reminded that the universe is far more dynamic, far more interconnected, and far more mysterious than we could have ever imagined. As we stand on the brink of a new era in astronomy, the tools we use to explore the cosmos are becoming more powerful than ever before. The next generation of telescopes, like the James Webb Space Telescope and the Square Kilometre Array, are not just incremental upgrades, they're game changers, designed to push the boundaries of what we can see and understand about the universe's earliest days. These instruments promise to take us further back in time than ever before, offering a glimpse into the cosmic dawn with a level of detail that was once unimaginable. The James Webb Space Telescope, or JWST, is already rewriting the rules of space exploration. Launched in late 2021, this cutting-edge observatory is equipped with a mirror over 6 times larger than that of the Hubble Space Telescope, allowing it to capture fainter and more distant objects. But it's not just about size. JWST instruments are optimized to observe in infrared light, which is crucial for studying the early universe. As light from the first stars and galaxies travels across billions of years, it gets stretched into the infrared part of the spectrum. JWST's ability to detect this light means it can peer through the cosmic dust and gas that obscure our view, revealing the faint glow of the universe's infancy. Already, JWST has delivered stunning results, capturing images of galaxies that existed just a few 100 million years after the Big Bang. These galaxies, though small and chaotic by modern standards, are the building blocks of the cosmos, the first steps in the universe's journey from simplicity to complexity. But this is just the beginning. Over the coming years, JWST will continue to observe these ancient objects, helping us understand how they formed, how they evolved, and how they contributed to the process of reionization. Meanwhile, on the ground, the Square Kilometre Array, or SCAR, is poised to revolutionize our understanding of the early universe in a different way. Unlike JWST, which focuses on light, the SKA is a radio telescope designed to detect the faint radio signals emitted by neutral hydrogen gas. This gas, which filled the early universe, emits a specific wavelength of radio waves known as the 21-centimeter line. By mapping these signals, the SKA will create a three-dimensional picture of the universe during the Dark Ages and the cosmic dawn, revealing how the first stars and galaxies ionized the surrounding gas and brought light to the cosmos. What makes the SKA so remarkable is its sheer scale. Once completed, it will consist of thousands of antennas spread across 2 continents, making it the largest and most sensitive radio telescope ever built. This unprecedented sensitivity will allow it to detect signals from the most distant galaxies, offering insights into how they formed and evolved. It will also help us understand the role of dark matter in shaping the early universe by mapping its distribution and tracing its influence on the formation of the first structures. Together, JWST and the SKA represent a new frontier in our exploration of the cosmos. They're not just tools for observing the universe, they're time machines capable of taking us back to a time when the first stars were just beginning to shine. And as we peer deeper into the past, we're not just uncovering the history of the universe, we're discovering the forces that shaped its evolution and set the stage for everything that followed. What will these telescopes reveal? Will we find evidence of the very first stars, or perhaps even the first black holes? Could they uncover new clues about the nature of dark matter or the origins of the cosmic web? The possibilities are endless, and the discoveries waiting to be made could fundamentally change our understanding of the universe's origins. As we look to the future, it's clear that these next-generation telescopes are more than just scientific instruments. They're windows into the past, offering us a chance to witness the birth of the cosmos itself. And with every new observation, we're reminded that the universe is full of surprises, waiting to be uncovered by those who dare to look deeper. The search for the first stars is one of the most tantalizing quests in modern astronomy. These ancient giants, born in a universe of pure hydrogen and helium, were the pioneers of cosmic illumination. Yet, despite their monumental role in shaping the cosmos, we've never seen them directly. Their light, though brilliant in its time, has traveled billions of years to reach us, stretched and dimmed by the expansion of the universe. Today, it's buried in the faintest whispers of infrared radiation, far beyond the reach of even our most advanced telescopes. But just because we can't see them doesn't mean we can't find them. Scientists are turning to clever, indirect methods to uncover traces of these elusive stars. One approach is to search for their remnants. When the first stars died, many exploded as supernovae, scattering their elements across the cosmos. These explosions left behind chemical fingerprint signatures of the first heavy elements that we can detect in the oldest stars and gas clouds. By studying these ancient relics, researchers can piece together the lives and deaths of the first stars, much like archaeologists reconstructing a lost civilization from fragments of pottery and stone. Another strategy is to look for the impact these stars had on their surroundings. When the first stars ignited, their ultraviolet light ionized the surrounding hydrogen gas, creating bubbles of transparency in the cosmic fog. These bubbles, though long gone, left imprints in the distribution of hydrogen that we can still detect today. By mapping these imprints, scientists can trace the locations of the first stars, much like following the ripples in a pond to find the spot where a stone was thrown. But why does finding the first stars matter so much? For one, they hold the key to understanding how the universe transitioned from darkness to light. They were the catalysts for reionization, the process that made the cosmos transparent and set the stage for the formation of galaxies. Without them, the universe might have remained a featureless void, incapable of supporting the complex structures we see today. Discovering the first stars would also provide a window into the universe's chemical evolution. These stars were the first to forge elements like carbon, oxygen, and nitrogen elements that would later become the building blocks of planets, life, and even us. By studying their remnants, we can trace the origins of the elements that make up our world, uncovering the story of how the universe grew from simplicity to complexity. The search for the first stars is more than just a scientific challenge. It's a journey to the very roots of existence. These stars were the universe's first light, the spark that ignited the cosmos and set it on a path toward complexity. Finding them would be like uncovering the first chapter of a cosmic story, one that connects the birth of the universe to the emergence of life. As we continue to refine our tools and techniques, the possibility of finding the first stars grows ever closer. With next-generation telescopes like the James Webb Space Telescope and the Square Kilometre Array, we're on the brink of a new era of discovery. And when that moment comes, it won't just be a triumph for science, it will be a profound reminder of our connection to the cosmos, a testament to the enduring legacy of the stars that lit the way. The search for the first stars is a reminder that even the faintest whispers of the past can hold the keys to understanding our universe. And as we peer deeper into the void, we're not just looking for ancient light, we're uncovering the origins of everything we know. As we peer back into the cosmic dawn, we're confronted with a tantalizing possibility. What if our universe isn't alone? What if it's just one thread in an infinite tapestry of universes, each with its own unique set of physical laws and conditions? This is the multiverse hypothesis, a bold idea that challenges everything we think we know about reality. And if it's true, the cosmic dawn might not have been a singular event, but one of countless cosmic awakenings, each unfolding in its own distinct way. The multiverse concept isn't as far-fetched as it might sound. In fact, it's rooted in some of the most advanced theories in physics, from string theory to cosmic inflation. These theories suggest that our universe could be just one bubble in a vast cosmic foam, where other universes exist alongside ours, each governed by its own rules. In some of these universes, the laws of physics might be so different that the cosmic dawn never happened, or unfolded in ways we can scarcely imagine. Imagine a universe where gravity is weaker, or where the fundamental constants of nature are slightly tweaked. In such a place, the first stars might have formed later or not at all. The process of reionization could have been delayed, leaving the universe cloaked in darkness for billions of years longer. Or perhaps in another universe, the first stars ignited in a blaze of light far more intense than anything we've seen, ionizing the cosmos in a fraction of the time. The possibilities are as vast as the multiverse itself. What makes this idea so fascinating is how it transforms our understanding of the cosmic dawn. If our universe is just one of many, then the story of its transition from darkness to light isn't just a cosmic event, it's a cosmic coincidence, one that happened to play out in a way that allowed galaxies, stars, and eventually life to emerge. It's a reminder that the universe we inhabit might be the result of a delicate balance of conditions, one that could have been entirely different elsewhere. But how do we explore these ideas when other universes, by definition, lie beyond our reach? scientists are turning to indirect methods, using mathematics and simulations to test the implications of the multiverse hypothesis. For example, if the multiverse exists, it might leave faint imprints on the cosmic microwave background, subtle patterns or anomalies that hint at the presence of other universes. Detecting these signals is a monumental challenge, but it's not impossible. The multiverse hypothesis also raises profound philosophical questions. If other universes exist, each with its own cosmic dawn, what does that mean for our place in the cosmos? Are we part of a rare, finely tuned universe or just one of countless possibilities? These questions push the boundaries of science, blurring the line between physics and philosophy, and inviting us to rethink what it means to exist in a vast, interconnected reality. While the multiverse remains speculative, it's a powerful lens through which to view the cosmic dawn. It challenges us to think beyond the confines of our own universe and consider the broader implications of its origins. Whether or not other universes exist, the idea reminds us that the story of the cosmic dawn is more than just a historical event. It's a window into the fundamental nature of reality itself. As we continue to explore these ideas, we're reminded that the universe is full of mysteries waiting to be uncovered. From the first flicker of starlight to the possibility of infinite universes, the cosmic dawn is a story of transformation, connection, and endless possibility. And in that story, we find not just the origins of the cosmos, but a deeper understanding of our place within it. To truly grasp the origins of the universe, we need to venture into the realm of the unimaginably small, the quantum world. It's here, in the earliest moments of existence, that the seeds of everything we see today were sown. Tiny ripples in the fabric of reality, born from the strange and unpredictable nature of quantum mechanics, set the stage for the cosmic dawn. These quantum fluctuations, no larger than a fraction of a proton, might seem insignificant at first glance, but over billions of years, they grew into the vast cosmic structures we see today: stars, galaxies, and the intricate web that connects them all. So, how did these minute imperfections in the early universe shape the cosmos we inhabit? The story begins in the first fraction of a second after the Big Bang. At this point, the universe was a seething, chaotic soup of energy and particles, governed by the laws of quantum mechanics. In this strange and volatile environment, particles and energy flickered in and out of existence, creating tiny fluctuations in density. These fluctuations were random, but they weren't random in a chaotic way. They followed the precise rules of quantum physics. Think of it like the surface of a calm lake, where tiny ripples form and disappear, leaving behind subtle disturbances in the water. In the early universe, these quantum ripples were the first whispers of structure, the faintest hints of what was to come. As the universe expanded and cooled, these tiny ripples began to grow. Gravity, the great sculptor of the cosmos, started to pull matter into the slightly denser regions created by these fluctuations. Over hundreds of millions of years, these regions grew larger and denser, eventually collapsing under their own gravity to form the first stars and galaxies. What began as a quantum whisper became a cosmic shout, echoing across the universe and shaping its evolution. We can still see the echoes of these early fluctuations today, imprinted in the cosmic microwave background, or CMB. This faint glow, the oldest light in the universe, carries the fingerprints of those quantum ripples, frozen in time just 380,000 years after the Big Bang. The CMB shows us a universe that's almost perfectly uniform, but with tiny variations in temperature variations that correspond to the denser and less dense regions seeded by quantum fluctuations. These are the blueprints of the cosmic web, the maps that guided the formation of everything we see today. What's remarkable is how something so small could have such a profound impact. The quantum fluctuations in the early universe were incredibly subtle, just one part in 100,000. Yet they were enough to set the stage for the birth of stars, galaxies, and the vast cosmic structures that define the universe. Without these tiny ripples, the universe might have remained a featureless void, forever dark and empty. But why did these fluctuations grow? The answer lies in the delicate interplay of gravity and expansion. As the universe expanded, the denser regions created by quantum fluctuations pulled in more matter, growing larger and more massive over time. Eventually, these regions became so dense that they collapsed under their own gravity, igniting the first stars and giving birth to the first galaxies. It's a process that's both elegant and inevitable, a testament to the power of gravity and the enduring legacy of quantum mechanics. The role of quantum fluctuations in shaping the universe is a reminder of how interconnected the cosmos truly is. From the tiniest particles to the largest structures, everything is linked by the same fundamental forces. The ripples that began in the quantum realm billions of years ago have grown into the stars that light our night sky, the galaxies that fill the cosmos, and even the atoms that make up our bodies. As we continue to study these early fluctuations, we're not just uncovering the origins of the universe, we're discovering the forces that shaped its evolution and set the stage for everything that followed. The story of quantum fluctuations is a story of transformation, of how the smallest beginnings can lead to the grandest designs. And in that story, we find not just the origins of the cosmos, but a deeper connection to the universe itself. The universe is a tapestry woven from the threads of quantum mechanics, gravity, and time. And as we pull back the layers, we're reminded that even the smallest ripples can create the most profound waves. The journey from quantum fluctuations to cosmic structures is a testament to the power of the universe's earliest moments and to the endless possibilities that lie ahead. The cosmic dawn wasn't just the birth of stars and galaxies, it was the beginning of a cosmic journey that would eventually lead to planets, life, and us. This pivotal era, when the first stars ignited and the universe transitioned from darkness to light, set the stage for everything that followed. But what does this ancient chapter of the universe's history tell us about the origins of life? Could the first stars and galaxies hold clues to how life emerged in the cosmos? When we look at the cosmic dawn, we're not just studying the birth of the universe, we're tracing the origins of the ingredients that make life possible. The first stars, though massive and short-lived, played a crucial role in creating the elements necessary for planets and life. Through nucleosynthesis, they forged carbon, oxygen, nitrogen, and other essential building blocks in their cores. When these stars exploded as supernova, they scattered these elements across the cosmos, enriching the universe with the raw materials for future generations of stars, planets, and even living organisms. But the story doesn't end with the creation of these elements. The process of reionization, driven by the light of the first stars and galaxies, also played a key role in shaping the conditions for life. By ionizing the hydrogen gas that filled the early universe, these luminous objects made the cosmos transparent, allowing light to travel freely. This not only paved the way for the formation of galaxies like our Milky Way, but also created environments where planets could form and thrive. Without this transformation, the universe might have remained a dark, inhospitable place, incapable of supporting life. What's fascinating is how interconnected these processes are. The birth of the first stars, the scattering of heavy elements, and the ionization of the cosmos weren't isolated events, they were part of a grand cosmic chain reaction. Each step built upon the last, creating the conditions for complexity to emerge. Over billions of years, these processes gave rise to galaxies, stars, and planets, setting the stage for life to take hold. But the cosmic dawn doesn't just tell us about the origins of life. It also offers insights into our place in the universe. By studying this era, we're reminded that the elements that make up our bodies, the air we breathe, and the planets we inhabit all trace their origins back to the first stars. We are, in a very real sense, the children of the cosmic dawn, shaped by the events that unfolded billions of years ago. This raises profound questions about the uniqueness of life in the universe. If the cosmic dawn set the stage for life here, could it have done the same elsewhere? Are there other planets orbiting distant stars where similar processes have given rise to life? While we don't yet have the answers, the study of the cosmic dawn brings us closer to understanding the conditions that make life possible. It's a reminder that the universe is not just a collection of stars and galaxies, it's a dynamic, evolving system, capable of creating the conditions for life to emerge. As we continue to explore the mysteries of the cosmic dawn, we're not just uncovering the history of the universe, we're discovering the story of our own origins. From the first stars to the planets we call home, this ancient era connects us to the cosmos in ways that are both profound and deeply personal. It's a story of transformation, of how the universe grew from simplicity to complexity, and how the seeds of life were sown in the hearts of ancient stars. The cosmic dawn is more than just a chapter in the universe's history. It's a testament to the enduring power of creation. From the birth of the first stars to the emergence of life, it's a story that reminds us of our connection to the cosmos and the incredible journey that brought us here. And as we continue to explore its mysteries, we're not just looking back in time, we're uncovering the origins of everything we know. As we trace the origins of the universe, one of the most puzzling characters in the cosmic story emerges: dark energy. This mysterious force, invisible and elusive, is driving the universe to expand at an ever-increasing rate. But its influence isn't limited to the present day cosmos. Dark energy may have played a subtle yet significant role in shaping the universe's earliest moments, including the cosmic dawn. So, how does this enigmatic force fit into the story of the first stars and galaxies? To understand dark energy's impact, we need to rewind to the universe's infancy. In the first moments after the Big Bang, the cosmos was dominated by radiation and matter, with gravity acting as the primary force shaping its evolution. But as the universe expanded and cooled, dark energy began to take hold. Unlike gravity, which pulls matter together, dark energy works in the opposite direction, pushing the fabric of spacetime apart. This cosmic tug of war between gravity and dark energy has shaped the universe's evolution, from the formation of galaxies to its ultimate fate. During the cosmic dawn, dark energy's influence was subtle but profound. As the first stars and galaxies began to form, gravity was the dominant force, pulling matter together into dense clumps. Yet, even in these early stages, dark energy was quietly at work, stretching the fabric of spacetime and influencing how structures grew. While it didn't stop the formation of stars and galaxies, it may have altered their distribution and growth rate, subtly shaping the cosmic web we see today. One of the most intriguing questions is whether dark energy affected the timeline of reionization. As the first stars and galaxies ionized the surrounding hydrogen gas, they cleared the way for light to travel freely. If dark energy was already influencing the universe's expansion during this period, it could have impacted how quickly reionization occurred. For example, a faster expansion rate might have made it harder for ionizing radiation to reach distant gas clouds, potentially slowing down the process. Alternatively, dark energy's influence could have created regions where reionization happened more rapidly, leaving pockets of ionized gas scattered across the cosmos. But dark energy's role in the cosmic dawn isn't just about timing. It's also about structure. The universe's large-scale structure, with its vast filaments and voids, is shaped by the interplay of gravity and dark energy. During the cosmic dawn, dark energy may have influenced how matter clumped together. affecting the formation of the first galaxies and the growth of the cosmic web. By studying the distribution of galaxies and the way they're connected, scientists can look for clues about dark energy's early influence, piecing together its role in the universe's evolution. What makes dark energy so challenging to study is its invisibility. Unlike stars, galaxies, or even dark matter, dark energy doesn't interact with light or matter in any observable way. Its presence is inferred from its effects on the universe's expansion, making it one of the most elusive phenomena in science. Yet, despite its mysterious nature, dark energy is a key player in the cosmic story, shaping the universe from its earliest moments to its distant future. As we continue to explore the mysteries of the cosmic dawn, dark energy remains a tantalizing puzzle. Its influence may have been subtle, but its impact on the universe's evolution is undeniable. By understanding how dark energy shaped the first stars and galaxies, we're not just uncovering the history of the cosmos, we're gaining insights into the forces that continue to shape its destiny. From the birth of the first stars to the accelerating expansion of the universe, dark energy connects the past to the present, weaving its influence through the fabric of space-time. And as we unravel its mysteries, we're reminded that the universe is full of surprises, waiting to be discovered by those who dare to look deeper. The cosmic dawn isn't just a scientific concept, it's a source of inspiration that has sparked the imagination of artists, writers, and filmmakers. This ancient era, when the first stars ignited and the universe transitioned from darkness to light, has become a powerful symbol of beginnings, transformation, and the mysteries that lie beyond our understanding. From the silver screen to the pages of novels, the cosmic dawn has found its way into popular culture, shaping how we think about the universe and our place within it. One of the most striking ways the cosmic dawn has influenced storytelling is through its portrayal as a time of profound change and discovery. In science fiction, it often serves as a backdrop for tales of exploration and wonder. Movies like Interstellar and Contact draw on the awe-inspiring scale of cosmic events, weaving themes of humanity's quest for knowledge into their narratives. These stories don't just entertain, they invite us to reflect on the vastness of the universe and the possibilities that lie beyond our current understanding. Literature, too, has embraced the cosmic dawn as a metaphor for new beginnings. Authors like Arthur C. Clarke and Isaac Asimov have used the birth of stars and galaxies as a canvas to explore themes of creation, evolution, and the enduring human desire to uncover the unknown. In their hands, the cosmic dawn becomes more than a scientific event. It's a moment of cosmic poetry, a reminder that the universe is full of stories waiting to be told. Even visual art has been touched by the allure of the cosmic dawn. Painters and digital artists have reimagined this ancient era, blending scientific accuracy with creative interpretation to create stunning depictions of the first stars and galaxies. These works often evoke a sense of wonder, capturing the beauty and mystery of a time when the universe was still young and full of potential. Through their art, they invite us to see the cosmos not just as a collection of facts and figures, but as a source of inspiration and awe. But the cosmic dawn's influence extends beyond fiction and art. It's also shaped how we think about science itself. Documentaries and educational programs often use this era as a starting point to explore the origins of the universe, framing complex concepts in ways that are accessible and engaging. By connecting the cosmic dawn to the bigger picture of cosmic evolution, these works help us see science as a story, one that's still unfolding, with new discoveries waiting just around the corner. What makes the cosmic dawn so compelling in popular culture is its universal appeal. It speaks to something deep within us, a curiosity about where we came from and what lies beyond the horizon. Whether it's through a blockbuster movie, a thought-provoking novel, or a breathtaking piece of art, The cosmic dawn reminds us that the universe is more than just a collection of galaxies and stars. It's a source of endless fascination and wonder. As we explore how the cosmic dawn has shaped our cultural understanding of the cosmos, we're reminded that science and storytelling are deeply intertwined. Both seek to make sense of the world around us, to uncover the truths that lie hidden in the darkness. And in that shared quest for knowledge, we find not just the origins of the universe, but the origins of our own curiosity and imagination. The cosmic dawn isn't just a chapter in the history of the universe, it's a mirror that reflects our deepest questions and aspirations. Through the lens of popular culture, it invites us to dream, to explore, and to wonder about the mysteries that still await discovery. And in that invitation, we find a connection not just to the cosmos, but to each other. As we journey deeper into the mysteries of the cosmic dawn, it's not just scientific questions that demand our attention, it's the ethical ones too. The pursuit of knowledge about the universe's origins is undeniably thrilling, but it also raises important considerations about how we explore, what we prioritize, and the impact of our discoveries on our world and beyond. How do we balance the drive to uncover the cosmos' secrets with the responsibility to protect our planet and its finite resources? And as we reach further into the stars, what obligations do we carry as explorers of the universe? One of the most pressing ethical questions revolves around the cost of cosmic exploration, both financially and environmentally. Building and launching advanced telescopes, space probes, and other instruments requires significant investment, often billions of dollars. While these projects expand our understanding of the universe, they also divert resources that could be used to address pressing challenges here on Earth, such as climate change, poverty, and healthcare. This raises a fundamental question. How do we justify the allocation of resources to space exploration when there are so many urgent needs at home? The environmental impact of space exploration is another critical concern. Launching rockets and satellites consumes vast amounts of fuel and releases greenhouse gases into the atmosphere. As the space industry grows, so does its carbon footprint, adding to the strain on our planet's ecosystems. This isn't just a problem for today, it's one that will affect future generations. To address this, scientists and engineers are exploring greener alternatives, such as reusable rockets and sustainable fuels, but the challenge remains significant. How can we ensure that our quest to understand the cosmos doesn't come at the expense of the very planet that makes that quest possible? Beyond the practical concerns, there's also the question of how we use the knowledge we gain. The discoveries of the cosmic dawn don't just belong to scientists or governments, they belong to all of humanity. This raises important issues about access and equity. Will the benefits of cosmic exploration be shared broadly, or will they be hoarded by a privileged few? And how do we ensure that the pursuit of knowledge doesn't exacerbate existing inequalities, whether between nations or within societies? There's also the philosophical dimension to consider. As we uncover the origins of the universe, we're forced to confront profound questions about our place within it. What does it mean to be a species capable of understanding the cosmos? Does this knowledge come with a responsibility to act as stewards, not just of Earth, but of the universe itself? These questions don't have easy answers, but they're essential to grapple with as we continue to push the boundaries of exploration. The ethics of cosmic exploration also extend to how we treat other worlds. As missions to Mars and beyond become more feasible, we'll need to think carefully about how we interact with potential extraterrestrial environments. Should we prioritize preserving these worlds in their natural state, or is it acceptable to alter them for human use? And if we ever encounter extraterrestrial life, even in its simplest forms, what moral obligations would we have to protect and respect it? These ethical dilemmas aren't just theoretical, they're already shaping the future of space exploration. organizations like NASA and private companies are increasingly incorporating ethical considerations into their missions, from minimizing space debris to ensuring that space remains a peaceful domain. But as the pace of exploration accelerates, these conversations will only become more urgent. Ultimately, the ethics of cosmic exploration remind us that the pursuit of knowledge isn't just about what we discover, it's about how we discover it. It's about balancing curiosity with responsibility, ambition with humility, and progress with preservation. As we continue to unravel the mysteries of the cosmic dawn, we're not just shaping the future of science, we're shaping the future of humanity. This journey into the cosmos isn't just a scientific endeavor, it's a moral one. And as we navigate its challenges, we're reminded that the universe isn't just a place to explore. It's a mirror that reflects our values, our priorities, and our vision for the future. The choices we make today will echo across the stars, shaping not just our understanding of the cosmos, but our legacy within it. The story of the cosmic dawn isn't just a journey into the past, it's a roadmap for the future. By peering back into the universe's earliest moments, we uncover more than just the origins of stars and galaxies. We gain insights into the forces that shaped existence itself. But how does this ancient era, billions of years removed from our present, hold relevance for humanity's future? The answer lies in the profound lessons it offers. Lessons about resilience, interconnectedness, and the delicate balance that sustains life. One of the most striking takeaways from the cosmic dawn is the power of transformation. The universe began in darkness, a featureless void filled with nothing but hydrogen gas. Yet, through the interplay of gravity, light, and matter, it evolved into a vibrant cosmos teeming with complexity. This transformation wasn't instant, it unfolded over hundreds of millions of years, driven by subtle but persistent forces. For humanity, this serves as a reminder that change, even on the grandest scales, is possible. Whether we're addressing global challenges like climate change or technological innovation, the story of the cosmic dawn inspires us to think long-term and act with patience and purpose. But the cosmic dawn also highlights the importance of interconnectedness. The first stars didn't form in isolation, they were born from the collective pull of gravity, the ripples of quantum fluctuations, and the delicate dance of matter and energy. Their light didn't just illuminate the cosmos, it transformed it, paving the way for galaxies, planets, and ultimately, life. This interconnectedness is a powerful metaphor for humanity's own journey. In an increasingly globalized world, our actions ripple across borders and generations, shaping the future in ways we may not yet fully understand. The cosmic dawn reminds us that we are part of a larger system, one where collaboration and shared responsibility are essential for survival and growth. Another lesson lies in the role of balance. The early universe was a place of extremes, vast clouds of gas, searing heat, and crushing gravity. Yet, it was the delicate balance between expansion and contraction, light and darkness, that allowed the first stars to ignite and the cosmos to flourish. Today, as we face challenges like environmental sustainability and resource management, this balance becomes more critical than ever. The cosmic dawn teaches us that thriving systems, whether cosmic or human, require harmony, not domination. Perhaps the most profound insight from the cosmic dawn is its reminder of our cosmic origins. The elements that make up our bodies, the air we breathe, and the planets we inhabit all trace their roots back to the first stars. This connection isn't just scientific, it's deeply personal. It reminds us that we are not separate from the universe, but an integral part of its story. This perspective can inspire a sense of stewardship, encouraging us to protect not just our planet, but the broader cosmos we are only beginning to explore. As we look to the future, the cosmic dawn offers a lens through which to view humanity's potential. Just as the first stars transformed a dark universe into one filled with light, we have the capacity to shape our own destiny. Whether it's through advancing technology, fostering global cooperation, or exploring the stars, the lessons of the cosmic dawn remind us that even the smallest actions can have a profound impact. It's a call to embrace curiosity, resilience, and responsibility, to not only understand the cosmos but to honor our place within it. In the end, the cosmic dawn isn't just a chapter in the universe's history, it's a mirror reflecting humanity's potential. By studying this ancient era, we're not just uncovering the origins of the cosmos, we're charting a course for our own future. And in that journey, we find not just knowledge but hope, a reminder that even in the darkest of times, light can emerge, guiding us toward a brighter tomorrow. The cosmic dawn stands as one of the most extraordinary chapters in the story of the universe, a time when darkness gave way to light and simplicity blossomed into complexity. It's a period that holds the keys to understanding not just how the cosmos came to be, but how we, as part of that cosmos, came to exist. From the fiery birth of the first stars to the intricate web of galaxies that followed, this era shaped the universe into the vibrant, dynamic place we see today. It's a reminder that every star, every galaxy, and every atom in our bodies carries the imprint of this ancient epoch. What makes the cosmic dawn so remarkable isn't just its historical significance, it's the way it connects us to the cosmos. By studying this pivotal era, we're not just unraveling the mysteries of the universe's origins, we're uncovering the story of our own beginnings. The elements forged in the hearts of those first stars are the same ones that make up our world and ourselves. In a very real sense, we are the legacy of the cosmic dawn, shaped by the same forces that shaped the universe itself. As we continue to explore this ancient time, we're reminded that the universe is full of surprises. Every discovery, from the faint echoes of the first stars to the intricate patterns of the cosmic web, brings us closer to understanding the forces that shaped existence. And with each new insight, we're not just learning about the past, we're gaining a deeper appreciation for the beauty and complexity of the cosmos. The journey to understand the cosmic dawn is far from over. With next-generation telescopes and cutting-edge technology, we're on the brink of discoveries that could reshape our understanding of the universe's origins. What will we find? Will we uncover the first galaxies, or perhaps even the remnants of the first stars? The possibilities are as vast as the cosmos itself, and the answers may hold the key to some of the deepest questions about existence. Thank you for joining us on this incredible journey through time and space. If you've enjoyed exploring the mysteries of the cosmic dawn, don't forget to like and subscribe for more adventures into the wonders of the universe. And we'd love to hear your thoughts. What fascinates you most about this ancient era? Share your ideas in the comments below. Until next time, keep looking up and remember, the universe's greatest stories are still waiting to be told. The cosmic dawn isn't just a chapter in the history of the universe, it's an invitation to explore, to wonder, and to connect with the cosmos in ways that inspire awe and curiosity. As we gaze at the stars, we're not just looking into the past, we're glimpsing the future and all the possibilities it